For those who would like to follow along at home, or you if you want to linger on a slide, there is a link there at the bottom of this slide and at the bottom of every slide of where I've posted the PDF for this thing. And I guarantee that you won't get it all because I won't be able to say it all because I've prepared about 3 hours worth of stuff, which I like to do because I like to get my brain around it, and then I don't have time to actually bring it down to the size of a real talk. So apologies in advance, but the slides are there so you can check the receipts afterwards as much as you like. Let's see, does this work now? Yes. So here is the AOT static analysis of this talk. In other words, I don't need to execute this talk before I analyze it. I'm going to first discuss the words that we use, especially the words static and dynamic. I think I got kind of curious after using them like my whole career without actually fully knowing what they mean, so maybe it's time to hazard some general definitions, and that might even help us think. The reality behind static and dynamic is the particular difficulty of computation, in my opinion, which I will try to defend, and maybe it will be useful to you as well. But then, because of the difficulty of computation, we need to do things besides just full computation when we can, and that's what static is about. Within the VM, the way this plays out is there are lots of little staticky things that we do internally, and they break down where the dynamism is constrained, even as it determines the static decisions. And then what happens is either there's a secret workaround where we don't even know that the JIT is transforming our program, we just know it got faster. And then there are cooperative workarounds, the simplest of which is if I load a class file, only the debugger can reverse that decision. I don't get to like monkey patch my class on the fly if I decide I don't like what's in it. So that's I would call that a good cheat. It's a reasonable restriction, and it lets everything go faster because of the restriction. So shall we go to break? I think I just gave my whole talk. All right, part one. Is there a clock on here? No clock. I should have brought one. Okay. The JVM, which we all know and love, and many of us here know it quite well, has a bunch of buzzwords on it, and I've just picked a bunch of buzzwords that are my favorite ones, and you could read them here. It does do compilation both before you run your program using JavaC and secretly in the JIT. Everything's virtualized, everything's managed, everything's type safe, except when you don't want it to be, so it's flexible as well. The encapsulation is fully preserved, except when you don't want it to be, because you can unlock things in reflection sometimes. It scales beautifully. It runs in a pretty small container, although it doesn't run as small as Go or C++ Hello World, but that's okay for us. But it does scale monstrously. The GCs are particularly good, GC folks. I love what you do. It runs on all kinds of platforms, including the important ones and including future ones, we believe. It's polyglot in many ways. It can support many languages. It's written in many languages. It's run in many lingospheres, if that is a word. It's run across the globe. In a word, it's flexible as well as being reliable. So let me try and group these terms into static and dynamic, since that's what my talk is about. And I will leave you to read this slide later because I just explained it to you, and it's just all the buzzwords we know. Maybe encapsulation preserving is a static kind of thing because it lets you know things before you run about what can get into your class and what has to stay out of your class. That might work. Maybe the virtuality is really a dynamic thing because virtualization involves, like, as we know, interpreters, because everyone knows Java is an interpreted language, right? I hope you didn't believe that. Okay, so you can try and say some of these properties of the VM that we all know and love are of a static flavor, and others are of a dynamic flavor. I think this doesn't work. So let's start by understanding our words, because naming is hard, everyone knows that, although it's very hard to come up with the right citation for who said that first. But there's indirect evidence of who said it, and I don't remember his name, but he's famous. Another famous person is Confucius, who said, the first thing we have to do is rectify our names, which is a beautiful, evocative phrase that's been expanded upon by philosophers in the centuries since. And I put in a link to something by Cao Feng that tries to situate that historically. But one of the interpretations of what Confucius was saying there is, let's talk about things in ways that don't confuse ourselves before we actually try to make policy, before we actually try to run things. And run things, he's thinking about government, but we're thinking about software. Socrates said something very similar. I think smart people are onto this. The unlovely saying not only has its own disharmony, but also places an evil into souls. So bad words infect us potentially with bad thoughts. And when I say bad, I don't mean a curse word. I mean a word that has some kind of a lie in it, or some sort of a twist, or some sort of ugliness that distracts us. As many of us know, mathematicians certainly know this, beauty is a kind of a heuristic to clarity. My take is that elegance is a sign of clear thought. Not always, but often. You can think of counterexamples, of course. But elegance that masks a murky idea at least is paying fake homage to clarity. It's trying to look like clarity. If I make an elegant expression, I'm trying to look like I'm thinking clearly, even if I'm stupid. So, at the very least, getting good names, getting the names right, getting the definitions right, that's a down payment on clear thinking. So, I also love etymology. I love Wiktionary.com. Go to Wiktionary. It's so awesome. I love it. I used it for the next several slides. So you can use things like Wiktionary and the study of etymology as another heuristic for how words go together, what their implications are, what their connotations are. If Socrates were here today, he would probably do the thing that got him killed, which is annoy everybody by making a question like, you folks seem really smart and you keep using interesting words like static and dynamic. Clearly, you experts must know their definitions. Please help me understand what they mean also. Can you explain what a static thing is? And then he goes on and cross-examines the person until he gets sentenced to hemlock. So, static, that one word. It's part of a loose word family, quite large, has many words, word children, or word siblings or cousins throughout many languages on the earth. In English, we have steadfast, stay, steady, stationary, stable, statue. Definition 1 in Merriam-Webster is exerting force by reason of weight alone without motion. What might motion be in our field? That's an interesting question. What would be motionless something or other involving a computer? The definition is negative. They tend to be negative. It's not moving. It's not changing. Oh, not changing. Oh, that sounds like immutability. Could that have something to do with immutability? Indeed. Keep listening. The Greek word statikos is really close to the origin. It stands on top of the Proto-Indo-European root ste. I don't know how they pronounced it. Nobody does. It means something to do with standing, standing on, standing up. Status means stood up, having been stood up in place. So your status is your state, standing, rank, position, both in Latin and in English. And there are the sources. So there's also, related to this word, understand. Understand has the word stand in it, so it's one of these static-related cousin words. But what is understand? Did you ever wonder what it means? If you're standing under something, it means it's going to fall on you or you're in the wrong place. Why does that mean you're thinking clearly? You ever wondered that about English? Well, actually, unter means in between or inter in Latin. Unter is Old English, so unterstanden means standing among. To understand something is to be statically standing amidst the object of your contemplation. You are right next to it, everything's within reach, you got it. It's all fully grasped, or at least graspable. The word intellect in English, in Latin, is the equivalent in Latin to the English understand. Intellego has a similar visual meaning. Did you know that words often have metaphors in them? They're built out of metaphors, that our words are not just opaque tokens, but they have some metaphorical power in them. This is a debatable thing among linguists, but I believe it. So intellego, to be intellectual and to intellectualize something, to understand it with your intellect means to, among the things you're understanding, be able to grab them, take them, select them. Again, it's like unterstanden. It's being in the middle of something and having everything within grasp. Well, I think that's lovely. That's something to do with static, isn't it? But that was probably a diversion. Our phrase static analysis comes from static and the word analysis, which again is via Latin, the Greek word analusis, which means unraveling, a breakup, a loosening up, bringing something into pieces. We would call it divide and conquer, wouldn't we? So a still understanding breakup, that's static analysis in terms of the root metaphors of the words. What about the other word? The other word has a much smaller word family, fewer cousins. There's dynamikos, which is Greek. The Latin word is potens, which is a completely different derivation. But they come from different Proto-Indo-European roots, which are on the slide. You can read it later. But the important thing is that it relates to power, powerfulness, potency, possibility, being able to know how to do things and get them done. And so there we have our English words, dynasty, dynamo, dynamite. Those are all words of power. In physics, a dynamic system is a moving one. There are interlocking causes and forces that make the thing move in an unpredictable way, in an inherently complex way. In physics, a static system have forces in equilibrium. It's much simpler to understand. For us, they are antonyms, and they also have to do with something like motion, which I would just say is unconstrained computation, stuff that you don't know how it's going to turn out, which is why you have to do it in the first place to find out how it's going to turn out. If you knew how it was going to turn out, you wouldn't need to spend the electricity and the cooling on computation power. So static analysis is one thing, and dynamic analysis a thing? I'll come back to that, but dynamic execution at least, evaluation, dynamic experimentation, dynamic programming, dynamic profiling, those are things. So here's our life in pictures as computer professionals. We have on the one side the dynamic stuff and on the other side the static stuff, and it's kind of puzzling how they go together. Orbital dynamics versus the statics of a constructed bridge where all the forces are in equilibrium. That thing in the back, the triangular thing, is like a bridge static diagram. Another bit of Latin. You've heard the term stare decisis, which means it's decided, let it stay. That's in the stare is in the static word group, and stare decisis means let's make a static decision. So that's something I'll come back to also. Is this one concept or two? Is it really motion or non-motion? For us, anything dynamic depends on a computation. Let's define that as what? Running the JVM, running a Turing machine, running a von Neumann machine. The corresponding static behavior does not need a computation. Well, clearly we're going to run something when we run a static analysis. It's not the same computation. Is there one concept? Maybe. Let's try it. Let's try that static just means not dynamic. Let's see where we get with that. We can test it. Non-static field depends on a dynamic base offset. Non-static class depends on a dynamic outer link. So that kind of works. Finality is another kind of staticness. So we have two static keywords in the Java language. Just to confuse ourselves, we have final and static. Oh, and we have sealed too. That's a third static thing. So let's say it's one concept with opposite applications. I do not pretend to tell a complete story. I'm just giving you a static analysis. It's a simplified model. Going back to physics, statics tend to be time invariant. You can find counterexamples to that, I suppose, but involves forces in equilibrium, not motion, but something called moments, which is a very mysterious physics thing that you learn when you're a physics undergrad. Static models are often linear, yay, easy. You can use them you can solve it with matrices. There are local solutions. There might be a bigger dynamic differential equation that surrounds all the outlying states around the static force configuration, but within it, you're within epsilon of some sort of equilibrium. I'll get to homeostasis in a minute. You can disregard the tiny vibrations of the atoms. You just put them out of the model, right? You don't worry, and just like within a computer analysis, you don't care about the address of an object physically. You abstract away from that. So there's always details that the model throws away, both above and below. When a rocket launches, there's good dynamics. When a bridge breaks, there's bad dynamics. Control theory also talks about statics and dynamic distinctions. Even pure mathematics talks about dynamical systems, which happen in some sort of a pure Platonic universe where you just iterate a function system. That gives you things like Mandelbrot sets, and I'll show you one in a second. So a system can be viewed statically or dynamically, depending on which states you model. If you're modeling the full system for some definition of full, maybe not the electrons in your data center, that's not your full model, but if you're trying to actually compute the full application, maybe that's a big model. A little model just tries to tell in advance what it's going to do. And you can query even a fully dynamic system for things like profiles. What are the common orbits? What are the common behaviors? What happens most of the time? That's a thing where you get a static approximation to a dynamic thing. And there's a range of designs for models that we use to think about things. We can, in thermodynamics, the model abstracts away from individual particle kinetics and just uses big statistics. Notice statistics, that's a static word. A statistic is a timeless roll-up of a bunch of atoms bouncing off of each other. And we can do this too. Key point, within a static model, there's usually a bounding box. If the system makes an excursion out of that bounding box, the model no longer applies. So like if the program runs out of memory, that's an excursion outside of a bounding box. You usually analyze it without worrying about out-of-memory errors. There's a continuum also, not asking only what you're modeling in a static model, but when the model is applied. Is this in the middle of program execution, before program execution, after? You have a choice of times. Usually the civil engineer is worried about when the bridge has been just constructed, whether it's going to stay constructed. He doesn't worry about the states while the bridge is being constructed. We worry about the states in Leiden, at least, while the program is being constructed. We want to make that be good too. So we're aiming at stuff that's not exactly analogous to what the bridge builder is doing. So when you hear static, ask yourself, okay, static, yes. Socrates is also asking, in what aspects is it static? Socrates also wants to know, when did you mean to start modeling the system? Where does your model apply? And also, what's the bounding box for it? What doesn't the model apply to? And so therefore, I would say, this is my venture, I think a static program analysis is an abstract run or a modeled run. You're trying to run the program on paper, a dry run, to tell what's going to happen beforehand without fully executing it. So which things are you modeling? As of when are you modeling? And how far can you run with it? What's the bounding box? When do you run out of steam? A final thing that you get from static models is a decision. That's an easy generalization. You want to not just run the model in a static analysis for your health, you want to make a decision about how to make the subsequent dynamic analyses work better. And that is a key relationship between the static and dynamic worlds. Bunch of examples here I'll skip. So changing the representation of your program for later dynamic execution will help. We know that. That's what JIT does. So a static model, an analysis should enable a static decision. So we can say stare decisis. This JIT method is good to go until it excurses from its bounding box, and then you have to de-optimize and re-optimize. That's the summary. I'm going to skip. So what's dynamic activity? Well, it's just running the program after all the static decisions are made, and also in conformity with any giant galactic level rules like the JVMS, the JLS, JavaDoc of API. But inside the JVM is doing whatever it likes as long as it's within the rules and hopefully useful. Static decisions also can tell the human user, I don't see any bugs in this program. Why static work is important. All right, I'm already 10 minutes behind. That's fine. Statics are cheaper than dynamics. The fundamental rule of dynamic systems is they're hard. They have chaos. They're complex. You can't tell in advance what they're going to do Otherwise, you would have already optimized them to do in advance what they were going to do, and then you wouldn't run them, right? That's the practicality of the theory, is that the halting problem and similar problems are undecidable for any kind of a interesting computational system, starting with Turing machines. Fundamental assumption is if you're going to use a static decision, hopefully there will be no big divergences. You need a plan of action if they can occur. This often works out in all fields. Barring asteroids, this rocket will get to the moon because we've statically computed its orbit. And we can do corrections on the way, too. So our bounding boxes have to do with computational complexity theory. So we try to stay within small computational boxes, even as we prepare to do things that might diverge, looping data center processes that might have to be killed because they've gone outside their bounding box. It's well known that this is hard to stop in advance, to prevent in advance from one or two of your processes to just go south. Turing tells us, yeah, guys, that I told you that was already impossible to predict these sorts of interesting computations in advance. So here's our enemies. These are the guys that threaten us when we're programming. First of all, there's the halting problem, which means that some problems take infinity to solve. So unless you have an infinite budget and you're willing to wait around, you can't solve a number of things. The halting problem for starting, and all sorts of interesting analysis problems, which I would call Rice undecidables, and Rice's theorem talks about this. I have a link to that later. Also something called busy beavers, which is just the sort of parlor game of asking for a machine of a certain simplicity, what's the biggest number it can output? But even the simpler, less infinite dragons are still pretty scary. Exponential algorithms are generally avoided. Although SAT solvers can be successful as long as they don't go south. You can't stop them from going south once in a while. That's part of the game. Smaller things like matrix multiply, that takes an exponent of 1.4 in the data size, which you might correct me and say 2.8, but that's because the data size is a square matrix. The exponent is about 1.4. So there's small things that are like polynomial bound, and we like those. But we're still scared of them. We don't like cubic algorithms. So there's another complexity class which we're more friendly with. There's linear and log binary search and sort and things like that. We do those all the time. Those dragons are our friends. But system complexity is just, it's hard to control. Many parts, many moving parts, emergent properties. We can make it better or worse by our practices. But there comes a time when you just have to run the darn thing. If we run it, by the way, we can gather a profile and gather information that a static analysis could not have told us. Profiles are strictly incomparable with static analyses. Once you run that Turing machine, you can actually empirically observe its behavior. And if you think that's stable behavior, stable is another static cousin, stable behavior, then it's worth speculating that it will continue. And that's why we do Leiden training runs. Here's a program. What does it do? Well, it's called the 3x plus 1 problem, if you've heard of that. How many of you have heard of the 3x plus 1 problem? Yay! Good. This is a good group. Can I optimize this Java program? I think I can turn that function call into start greater than or equal to 2. A math person will tell us yes, but how do you know? Maybe a smart enough compiler, right? Or does it loop infinitely? Does it always get down to a low enough number that you exit from the program? And the math people tell us we don't know. We have tested it up to 2 to the 70. So this program, because it uses 64-bit longs, does terminate. And I've tweaked it to terminate on overflow. So we're okay there. But it's the Collatz conjecture is what the 3n plus 1 problem is. It appears to be beyond today's math. This simple program, you can't tell whether you can constant fold it or not because it might not terminate. Busy beavers, a whole other one. I'm going to let you explore that offline, but busy beavers are awesome. We have solved the halting problem for Turing machines up to size 5. 5 states. That's a little simpler than the call-outs conjecture I showed you a minute ago, probably, but it has call-outs like behavior, which is scary. And eventually you get into like undecidable and full Turing compute structures built on top of call-outs like function systems. That's why Diophantine equations are impossible to solve in general. BB6, huge number of steps, take more than the length of the universe, 10 to the 10 to the 10 to the 10 to the something steps at least. The Riemann hypothesis can be proven or disproven by examining the halting behavior of a approximately 750 state Turing machine that's been constructed. Our programs aren't that simple either. Maybe they're not as pathological as a busy beaver, but once in a while they decide to go and beaver off into the abyss. So your program might malfunction. This is true for any powerful enough function. Are there exceptions? I can give you 2 of them. If the static analysis secretly runs your program, then you can say, see, it works. I know what it's going to do. But that's cheating, right? It's as expensive as doing it the right way. Or if you have a really tame program like a finite state machine, a regular expression thing, then its options for misbehaving are less. In practice, we try to write tame programs, typed, well-structured, unit-tested, but we can't bet the whole farm on purely static analysis. Dynamism gets a vote. That's why we do actual imperative testing. So in our life, we're dangling above the abyss of Turing machine behavior, but we don't give up on static analysis as a result. We use it when possible, but we don't trust it 100%. If it applies a static model, we might get unlimited benefit for future runs. If it doesn't apply, then we got to go with dynamic testing. There's some links for Rice's theorem, including Rice's theorem for managers. If someone wants you to invest in their thing and they tell you they've solved Rice's theorem, they've disproven it, they've found a counterexample, then don't invest. And if your direct reports tell you, I know how to foolproof have the data center tasks never ever go out of bounds, have a grain of salt on that one too. For us, there's a couple links I loved finding on the web, some grad school stuff. So a static analysis makes a dry run of a model abstracted somehow from a full program. It's not the whole program, it's just abstraction. And being an abstract model, it is simpler and faster. By the way, even full programs are abstractions because they run on top of electronic systems. We have to choose a model that is not too rich and not too poor. Some definitions there. But the goal is let's build out efficient and informative static analyses, and let's also build out the dynamic experiments that cover the gaps. A static analysis can be very aggressive. It can try and ride the dragon. It can have a SAT solver inside of it if you really want to be heroic. But our experience tells us that there are limited opportunities for that. The smaller ones are better more often. So let's do the cheap ones. The JVM gives us some winning reasons to use small analyses because most JVM effects are constrained within some sort of local horizon or bounding box. There are exceptions like class loader constraints, and those are kind of just dynamic, and you try not to worry about them. Dynamic analysis, bonus slide. I don't think it's a thing, although I don't mind if you say it. I think it's really running something to gather information for a static analysis. A compromise on dynamic versus static is homeostasis, where you stay within some sort of a bounding box for very complex reasons, maybe reasons you don't even understand. And that's why profiling kind of works, because I think programs usually are homeostatic in some way until they do a phase change. Then they're homeostatic in a different orbit. Let's get to the cheats. Those are the fun part. So how does a JVM cope with these realities? Well, it welcomes cheating as long as you don't get caught. Famous quote by Peter Deutsch. Again, that's hard to find him saying that, but it's attributed. It's like naming is hard, one of those quotes. Implementing a language like Smalltalk efficiently requires the implementer to cheat. But that's okay, as long as you don't get caught. Good, let's cheat. We do cheat, don't we? We love cheating. And it's true not just in the virtual runtime, but also in when you're building abstractions on top of it in JDK, in Java code. You cheat inside. I invented the @stable cheat, but nobody can catch me because those are all private variables and they're properly state changed within the JDK. So cheating is, don't get caught means don't let the user see a deviation from the standard. And there's a longer version of it which says, in essence, that the great kind of cheating is either caching or representation changing. And caching is a kind of representation changing. What does Deutsch mean by representation changing? Well, he invented the JIT. It means JIT for one thing. I think he invented the JIT. It means changing the representation from a bytecode interpreter, even midstream, into object code. That's a pretty cool trick. Shall we try that? So the JVM cheats by building static models and static code dynamically. That's kind of the Deutsch got the ball rolling in a significant amount on this. Now these cheats can be done online or offline. They can be done JIT or AOT, but they're the same cheats, packaged differently. Everything is still done according to external standards. You don't tell your neighbors that you're cheating. Now, observations from the past can trigger a static analysis to make a decision for the future. That's an important flow there. I want you to keep that in mind, please. Any optimization can kick in at any moment where there's evidence for it, and that evidence can arise by chaotic dynamic processes. But once you have the evidence, you make a static decision, and then that constrains the future computation to be tamer and less like a dragon. We use a lot of static models in the VM. Profiles, the class files themselves are models if you look at them from the right angle. Constant pool states are a very important model that people don't appreciate. The constant pools are like always growing more and more static information as they resolve. So any kind of model in the JVM is some kind of computation that abstracts information about what's happened so far or what may happen in the near future in order to improve future execution, as long as the neighbors don't hear about it. So once again, JVM static models, what thing gets modeled, as of when does it get modeled, how far do you go with the model, how far does it go, and what happens when the model fails? What happens when do you need to de-optimize if your compiler speculated the wrong static condition? There's a lot of examples of that in this slide. I'll let you read it later. And then finally, the decisive question is, what do we decide? Why did we model it? What decision are we making to hopefully improve our future execution? So the decision might transform an interpreted method to a compiled method, or it might introduce something completely fresh and new, such as loading a new class, dynamic class file loading. That obviously fits in with this general dynamic model of execution. Bootstrap method execution. I love bootstrap methods. I don't know why, but when I first saw them, I loved them. Bootstrap methods are another kind of class loading, if you look at it right. They're the introduction of new computed behavior into the execution, and they do embody permanent decisions. So maybe loading something completely new in the program is static synthesis. Synthesis versus analysis. Maybe not. Depends on how specific you want to be. But it feels like some things are introduced like from outside and other things are evolved from inside. But in both cases, you do static modeling and then decisions, and then the thing becomes more tractable, more tame as you go into the future. The JVM does lots of its time doing dynamic stuff, especially during startup. Dynamic configuration everywhere. It's powerful. We love it. It gives us lots of ways to get our work done. The resulting configurations tend to be static decisions. I mean, there's mutable dependency injection, but most dependency injection tends to be static. Final, immutable. Along the way, the JVM looks at itself and gathers data, and your program may also gather data. You may do logging. You may have application level logging that tells the application what it needs to do next time. So there's modeling going on. In the end, though, if everything works right, when the JVM reaches peak performance, it reaches peak because it's spending almost all of its effort on the work you want done, as opposed to navel gazing or loading or garbage collecting. it's doing exactly what you wanted it to do. So that's a very narrow bounding box, and hopefully it stays in that bounding box, but we're ready if there's an excursion. So imagine a turbulent river flowing along, but it's slowly getting iced over in two ways. Some ice blocks fall onto it from above, boom, and that quiets some of the chaos of the river. More subtly, other ice forms from the material of the river itself, and that slowly dampens down. That's a phase change, or let's call it a representation change, slowly damping down the variability of the river. In the end, there's just one kind of a linear flow of the river. It's all constrained by the ice. And I want you to think that those are like in the JVM, those are all the static decisions that have been made, constraining the dynamisms until it's doing exactly what you want. And that's what peak performance looks like. Here's a state diagram of the same thing. You start with wildly dynamic execution. From that, you make observations about data, metadata, code. Maybe you cut off the wildly dynamic execution and you just look at the input program. That's the classic static analysis where there's no code run at all. But I'm saying in general, there has got to be some kind of a dynamic execution. The process of writing code is wildly dynamic. It involves human beings. But at some point, there's an analysis, a modeling, and a decision, which is intended to be a sticky decision. Outcomes, modified representation change, data, metadata, code, and then you have a tamer execution. And you repeat that process. There's a bunch of configurations. The static analysis could be AOT, which is offline, or JIT, which is online. It doesn't matter. You can do the same analyses both times. That's why Leiden uses so many of the dynamic capabilities of the VM to do its work. It's just using dynamic JIT-y stuff to do AOT work as well. It's a repackaging of the static analysis, both online and offline. It can be iterative or it can be single. It can be, as I said earlier, it can be heroic. You can do a SAT solver that's going to take all day. And maybe that's not online. Yeah? Maybe that's a beforehand packaging of your program. Or it can be some log-n process to analyze your model, and that can be done online. There's a case study for you to look at later. Static fields and classes. Here's how I think that fits in the model I've been advocating here. Static fields, especially final fields, obviously, or even speculatively static fields, not quite final fields, but stable fields. They can be modeled. There's a bounding box. There's decisions you can make based on that. Class hierarchy analysis, the same thing. You look at the classes. It's mostly true, but you don't know for sure if the classes will change or not. Maybe you're going to load new ones. Probably you're not going to unload them. Probably the debugger is not going to get in there. Otherwise, everything gets turned over. So you can say, well, I think we're in an orbit here where this class will always have a unique subclass. So I think I can make certain improvements to the structure of my computation as a result. If something changes, then you have to de-optimize. That was one of the big engineering pushes early in the life of Hotspot, was to support various kinds of state changes, de-optimization and re-optimization. I'll talk a little bit about, in the remaining time, which as I calculate is about 15 minutes, about not so sneaky cheats, which are really rule changes. If you don't like the game you're playing, you can cheat, or you can turn the table over and demand to play a new game. So now I'm going to talk about playing new games where static is more of an option. Static buys you more. Static is something that we embrace. The VM is already full of these things. They're sort of hiding in plain sight. There's a large number of static decisions, rules, constraints in the as of Java 1.0. Strong encapsulation tells you that the effects that affect code and state can be limited within a certain scope in many cases. Class file loading, the way the system dictionary and class loaders tango together, once the system dictionary gets a definition, it's irrevocable except for debugging. So that's, imagine if we'd done the JVM where you could reload a class at any moment. We'd have a very different optimization story, wouldn't we? We wouldn't be as far along. Many things are static in the VM. Just the thing that says you can't read a local variable until you write it, that's a Java C static analysis. We're used to it. We like it. It tells us something about the quality of our program, but also it tells the VM that it doesn't need to worry about uninitialized states. So that's a 2-for-1. Many of these checks that are in Java have a 2-for-1 benefit. They tell you something good about your program, and they tell the VM something good about the program. So we've always had to cooperate with these things. In Smalltalk, such conditions like a variable is not initialized yet probably need a cheat under the cover at the VM, and you don't get the benefit as a programmer being told your program doesn't have those sorts of bugs. Type descriptors, that's a static thing in the VM. How many know what a type descriptor is? Oh, come on, you're being shy. Everybody knows what that, no, some people don't have to know what it is, but it's just the type information, the string formatted type information in the VM that makes everything fit together, and you don't have to re-verify types on every API call. So that's a static thing. Indy, let's talk about Indy. That's got some static stuff in it, even though it's called dynamic. Invoke dynamic. Couldn't be static, right? There's already an invoke static. Well, we start with a invoke dynamic instruction with an associated constant pool entry, which specifies a bootstrap method and some static arguments. There's the word static there. So Indy has a static thing already. The whole schmear, the Indy instruction, the constant pool entry, the bootstrap method, and the arguments, those are all symbolic. Heuristic. If I hear symbolic, I know it's probably statically analyzable. Even though it's sitting in the middle of a dynamic mess of a VM application, it's sitting there in potentiality. It hasn't been potentiated yet. It's just a symbol. And then what happens when invoke dynamic is resolved, the bootstrap method gets invoked, and that yields, once more, a static decision. It says, this particular Indy is now not only statically associated with a symbol, that symbol has been consulted exactly once, and now there is a behavioral static property associated with it. It's just as good as neighboring bytecodes. The whole thing inlines. It's as if the class file grew a bunch of bytecodes instead of the Indy instruction. Bytecodes are static, right? You can't patch those babies. That would be fun. Should we try it? No. All right, so resolution time is the first Indy execution. But when you have another heuristic, when you have a symbolic thing and you can have a static analysis on it, that thing is shiftable. Indy is specified to run it as late as possible. But what if you could see that a bootstrap method there was no difficulty with shifting that bootstrap method to the beginning of program execution, or even before at AOT cache generation time, which is what Leiden does. This is why Leiden gets good improvements on Lambda-bearing code, because all those bootstrap methods execute in the AOT cache generation. So it turns out that if you have a symbolic, statically analyzable representation of a piece of your program, one Indy instruction, that becomes something you can shift around and put in a place that you prefer, which is in AOT cache generation, long before you run your program. You might have thought that Indy was a poorly designed instruction because it has to do all this crummy stuff ahead of time. Bootstrap methods, gee, I mean, you can't just execute the expression. You have to do a reflective thing. That's horrible. Well, the VM does that all day long. That's how it works. That's how symbolic resolution of all sorts works. That's how class loading works. The reason it's okay is these are computations that you can statically do ahead of time because they're simple enough, they're tame enough. Running a bootstrap method, not everybody's bootstrap method, right? You can have a bootstrap method that reads the network, but some bootstrap methods, including the ones that the JDK defines. So let's use more bootstrap methods. I think bootstrap methods, there was an original proposal for invoke dynamic, which says, do something like Smalltalk. Then we win. And that's what Guy Steele would call in growing a language. Have you heard of that talk before? Growing a language, he says, we don't need more vocabulary in our programs. We need more rules. We need generative compositional stuff. We don't need 5 new syntax triggers. Invoke this method like Smalltalk was an initial vision for invoke dynamic. That's why it's called invoke dynamic. And that would be like one more piece of vocabulary. Instead, I got a project by accident, and I said, you know what? I like Guy Steele's philosophy. Let's do something generative and compositional and something that can give us the next 5 or 10 bytecodes instead of just one more bytecode. Indy is the universal bytecode. The BSM tells the bytecode exactly what it's going to do, but it's just as compilable statically as any other bytecode if you know the bootstrap method. So that's where Indy came from. It's a growing the language move for the VM. Do you know that we could grow the VM? We have a growable VM as well as a growable language. Did you know that our growable language grows on top of our growable VM? That's why Lambda expressions were not new bytecodes or new attributes. They were just, thank you, Brian, bootstrap method invocations. Yes. And we can play it some more. Let me give you 3 places where we could play it some more. We could have lazy statics. We could have a field that needs to have a constant value associated with it, but we're not willing to assign that at any given time. We want to put a bootstrap method on that field. And the bootstrap method runs just like Indy does to give the static its value whenever it's needed. And that might be at the latest possible moment, or if you can statically analyze the bootstrap method. Are you seeing a pattern here? You can move it back to Leiden AOT cache generation time. It's your choice. And you can check the dynamics of the program by running it in a training run to see if it's worth doing or not, right? If it's never used, it's not worth doing it. You keep it lazy. But if it's used a lot, then you initialize it early. And it's all based on being able to symbolically analyze the bootstrap method for that particular lazy field to see whether he can be put into the AOT cache or not. Just like the Lambda metafactory invocations that we do today. Mindy. Mindy is method definition dynamic. Mindy says, okay, I'm going to have a native method. That means no bytecodes in it. A native method, but it's not going to call JNI. It has an attribute on it which says, forget JNI. The attribute is a bootstrap method. What does the bootstrap method do? Well, it makes a method handle of the required shape, and that's the body of the method. That's it. There are several uses for this even today. For example, it would be the most natural way, in my opinion, to build Babylon reflected methods. There'd be one representation based on a bootstrap method expression, and then that either gets executed directly or reflected and further processed. And then the big one, the parametric VM, which maybe you've seen. It's a proposal I did around COVID time when I had lots of time at home. And it's one way to have the VM support not only reified generics, but also type classes and 50 other things, because it's a growable strategy. It defines a new kind of connection between use and definition of any API reference, constructor, field, class, instantiation, method call. There's a new channel, which is a static channel, which passes from caller to callee, the caller's expectations of what the caller thinks is happening, to the callee in a form which is statically settable. It's a one-time decision per call site. So these call sites have different decisions about whether they're doing list of string or list of int. And then the common code in list has a static parameter which is set differently depending on who's calling it. That's the essence of it. And that static parameter could be a type argument. It could be a type class. It could be something completely different. It could be a sort algorithm knob. It could tell you whether you're doing flat arrays of complex or boxed arrays of strings, but with case-insensitive sorting. Have the same sort algorithm with different static knobs that are set differently at different use points. That's what the parametric machine buys you. That's why it's a growing the VM move. I put in a few slides about stable because I'm sorry I missed the workshop yesterday, but here's my input. So this is how stable works, except for the Leiden parts, but you can read the link to even find out about the Leiden parts. Stable means it's a cheating, sort of lazy, but don't look at it too hard, variable that is eventually constant. But stable, that's a good word. That's another one of these words in the static group. It has to do with the ste, Indo-European root. As a term of art, a stable thing is consistent in the sense that we can optimize on it. That's all it means. That's kind of a weak user model, right? Optimizable. Just make your code optimizable. That's the user model. We could save a lot of university education if we could just action that one statement. The VM is willing to bet its object code that a stable variable or a stable type or a stable behavior, a stable condition is going to stay stable within a bounding box, ready for de-optimization. You bet your code on that optimization. That's a stable thing, and a stable variable is an instance of that general idea of stable. Any condition can be stable. So I think we have now and can make more APIs for working on stable conditions of various sorts. I'll just point out the mutable call site. That's a stable behavior that can optionally be associated with an INDI. INDIs mostly have constant call sites, which are fixed and final and fully static. But a stable mutable call site can be changed, and that causes the compiler to have to re-optimize. And there could be future APIs too, which I will not talk about right now. What about rule changes for Leiden? Amazingly, because we repackage a lot of our JIT stuff into AOT form, there's been very little changes to rules for Leiden. This just surprised me. I assumed Leiden would have to go and change a lot of rules in order to get static analysis and good AOT analysis. But it's not been true. Except if we want to move forward, this is pulling more on the string that Dan mentioned in the previous talk. If we want to do user-defined classes with user-defined initialization logic and initialize those into the AOT cache, then we're going to need a user model for defining what are AOT-safe initialization activities. And that just brings the Turing dragon right back into the mix, and he's breathing fire over the whole thing. And this is why you can't AOT initialize your classes yet, but trust us, we want to do it. There are languages like Zig that sort of know how to do this all day long. And we are envious of all good languages in Java. We want to pull in Haskell type classes. Maybe we'll pull in Zig initialization expressions too at some point. We hope to share our experience at the very least outside of the JDK. We're still grappling with what it means to statically initialize the JDK itself. It's going to need refactoring. I think your code will need refactoring if you ever statically initialize it as well. Ordinary static finals, well, what if we just allow someone to patch the static final? That would solve a lot of problems. Well, it would also break the language. So remember when I said we fulfill all standards relevant to the language, we cheat but we don't get caught? If you change the rules, it's better if you don't change the fundamental rules while you're changing ancillary rules that are helping you optimize. So for Leiden, we're probably not going to upend the semantics of static finals. You get to set them in the AOT cache, or you get to set them in production, but not both. Seems fair, right? What about Valhalla rule changes? There, we thought we were going to need big rule changes, new bytecodes, everything. It turned out we didn't need that exactly, but we still need to change a lot of subtle rules. So that's why Valhalla has been the longest running project, I think, in the whole JDK. It's because the rules need very delicate and subtle changes because of the object model. We have to undo some accidental features of the object model. Compatibly, of course. Generics are even harder because of erasure. So, I mean, that takes us back to the parametric VM. Maybe that's the rule changes we need to fully roll out Valhalla with specialized generics. John Backus, years ago, wrote that he thought that all conventional languages, and he meant Algol and Fortran, are based on the limitations of the von Neumann machine, which is something that can patch any computed address at any time, at any moment. Does that sound like a dragon to you? That's what a Turing machine does. It patches any point of the tape. Well, it has to get there first, a bunch of shift operations, and then it patches whenever it wants, and then it goes forward from there. That's why they're complicated. Von Neumann machines are complicated because they do side-effecting arbitrary assignments into almost arbitrary places. This is why Backus he was an inventor of Fortran. This is why he went the other way and said, I think, in his Turing Award lecture, we need functional programming. Does that sound like Java has taken a page from that? All the stuff about immutables, everything I've been saying about static decisions, that's the genius of functional programming, part of it. Polymorphism is another genius. But by the original sin of Fortran, according to Backus, was splitting the world into expressions, which compute values, and statements, which feed stuff to that stupid von Neumann bottleneck you got hanging there. If we could have, suppose we could have write once memory. We know what static single assignment is for registers. What about static single assignment for memory? Suppose our routine work, there are always exceptions, like a Clojure program might have 5 state variables that are fully updatable, but the rest of it's all single assignment. What do I mean by single assignment? I mean that when you make a data structure, you write its components, and that's the only thing that ever gets written to the memory of that data structure. That's static single assignment for memory. That is a cure for an out-of-control von Neumann machine. I think Backus would like it. I think he did like it. That's why he gave his Turing machine his Turing Award lecture. So I think there's something here for us. We have to rectify our language. They knew it all along, those guys, Confucius and Socrates. Our words have to be in accordance with the full nature of our programs. We can't be fooling ourselves with our words. Otherwise, as Confucius said, our progress cannot be made. We cannot carry our computations on to success. It's true for our terms of art. We need permissive and flexible mental models for what static and dynamic means, not narrow definitions for specific, like C++. Oh, that's a static language. Java, that's a dynamic language. This is true also for the words in our programs that are in our programming languages, both in the source level and at the class file level. So growing a language, growing a VM. We need richly expressible, compositional, high-level rules, what Backus calls combining forms. He knew that from inventing Fortran, that this thing has such terrible combining forms. The first Fortrans didn't even have subroutines. Guy told me it took a long time before they even added basic creature comforts into the language. Even Algol had a Turing bottleneck in it, sort of encoded into the structure of the language. And Algol wasn't that great. But in any case, in our languages and our VMs, we don't want single-purpose lumps of sugary, what Guy calls vocabulary. We want rules more than vocabulary. Sugary lumps of stuff like XML literals in your favorite language. That's vocabulary, not rules. Or the thing I mentioned earlier, the invoke small talk instruction, which is what invoke dynamic was originally slated to be. What we want is dynamism, yes, full embrace of dynamism, but that can be iced down into predictable, powerful static decisions. And for that, I prescribe BSMs at the VM level. So here are the things we learned. We're out of time. Static analysis uses static appropriate inputs to make a model and then a decision for future dynamic execution. Those dynamic executions are hard to tame, but real program runs enable the best decisions. And of course, they pay our bills because we eventually have to make the computation. So we need an interlocking state diagram with loops in it even. I didn't put the loops on my state diagram. I should have. I put them verbally. We need interlocking static and dynamic passes in the JVM, which is a great platform for expressing this stuff and can be even better in the future if we make more things dynamically computable and then statically decidable. Secret cheating is great. Some static decisions need to be visible to users, like once you do this, you can't do it again. This lazy variable is not a von Neumann variable. You can't just patch it when you get tired of the current value. So there's a contract that says, decide once, move forward. Or decide once, but you know it's going to be expensive if you try to reverse that decision. It's like class value.clear is an example of something that's painfully expensive to do. So our JVM and our code, our language, and our libraries, they give lots of opportunities today for this, and I think what we need to do even more, this is a good pattern to embrace in the future as well. Savvy code participates in static decisions for the win. Yeah.
I would add that we have another thing, which is we have the bytecode that was designed as something that you can run, but we use it as an EST. And you have exactly the same thing with method handle, that you design to run, even I was not, even if I was disagreeing with this. But you consider it as though as an EST.
Yes. So what you're asking is, what is the status of these designs where there's an AST inside, but it's only executable from the outside? Yeah, so method handles, wouldn't it be nice to crack a method handle and look inside of it and then transform it based on its syntax? And that's what Peter Deutsch was talking about with representation changing in the Smalltalk runtime. A program was looking at its internal stuff that normally isn't available, but the program can change it and move it around. The JIT is able to crack the method handles. The JIT sees the AST. There's a conscious decision on my part not to give users too much ability to look inside the method handle because there's a cost to that. It creates contracts that may be difficult to optimize around. So there's a yin-yang there, as with static and dynamic. Do I have to run the method handle tree? I know it's an AST inside. Can I just look at it before I run it? That's a static analysis. Or do I have to run it? The answer for method handles is only the JIT gets to run it. What I'm suggesting, though, is there may be places where crackability is a useful add-on, even with specific contracts. So just as we have crackable lambdas in Babylon, that's an example of this new thing. You didn't used to be able to ask what are the bytecodes of your lambda or your method. Now you can. Method handles too, maybe. Thank you.